During the last lecture, I proved this lemma, which says that if W is an open subset of Rn or Rn plus, and it is equipped with two metrics, G and G bar, where G bar is Euclidean metric, then if K is a compact subset of W, then there exist two positive constants, C and capital C, such that for each point in K and each vector in Tx Rn, this chain of inequalities holds. Today I want to use this chain of inequality to prove another lemma, which says the following. Let Mg a Riemannian manifold with or without boundary. Let the dg be the Riemannian distance function suppose that U is an open subset of M and P is a point of U, then P has a coordinate neighborhood V with the property that there exists positive constants capital C, capital D, such that 1, if Q is a point of V, then dGPQ is smaller or equal than capital C multiplied by dG bar PQ, where G bar, exactly as before, is the Euclidean metric, and second, if Q does not belong to V, then the distance dGPQ is larger or equal than capital D. Unfortunately, I have to erase, and let's try to prove this result. So suppose that W is a neighborhood of P such that W is contained or equal to U, and there exists smooth coordinates x1, x2, xn on it. Using these coordinates, we can identify W with an open subset of Rn or Rn plus 1. Suppose that K is a compact subset of W containing a neighborhood V of P such that the following holds. If P belongs to the interior of M, let's write this way, then K can be the closure of a ball of center 0 arrays epsilon, and V can be simply the open ball of center 0 and raised epsilon. Instead, if P belongs to the boundary, then we can choose the intersection of this closed ball with Rn plus and V, the intersection of the open ball with Rn plus. This is the first inequality I want to prove. Unfortunately, I have to erase. Now, suppose that C and C bar, capital C, are the constants which appear in previous lemma and in particular for which this is true. This implies the following. If gamma is an admissible curve whose image is contained entirely in D, then C times the length with respect to the Euclidean metric of gamma will be smaller or equal than the length of the same curve with respect to G, and this will be smaller or equal to the length, the product of the constant C times the length of the same curve with respect to G bar. Why this is true? Because to get the length of a curve, you integrate the length of gamma prime. Now, the length of gamma prime satisfies C times the length of gamma prime with respect to G bar, smaller or equal than the length of gamma prime with respect to G, smaller or equal to C times length of gamma prime with respect to G bar, and the same chain of inequality will hold true for the corresponding integrals. Now we want to prove that goals show that if Q belongs to V, then the distance with respect to G of Q from P, this is smaller or equal to C times dG bar PQ. So let gamma be the parameterization of the line segment from P to Q. Then we have that C dG bar PQ will be equal to C times LG bar gamma. This is true because we are looking at a line segment. So the infimum of the length of piecewise regular curves joining P to Q is achieved by such a kind of curve. And this says that this distance coincides with this length. But now we use this inequality here. So I can write this way, and by definition of distance of P of Q from P, this will be larger or equal than the GPQ. Why? Because the distance is defined as an infimum, and here we are looking at just the length of one curve, so it is clear that this inequality holds true. So this says that dgpq is more or equal than a constant times dg bar pq. This is exactly what we wanted to prove. Now we have to prove that if Q does not belong to V, then dgpq is larger or equal than D. Now, in order to do this, once again, we suppose that gamma is a parameterization of a curve let's write properly. Precisely the parameterization of an admissible curve joining P to Q, and let T in AB denote the infimum of times T in AB. Sorry, I made a typo. This is T0 of T in AB, such that gamma T does not belong to D. So this implies that gamma A T0 is contained in K, and the distance with respect to Euclidean metric of P from gamma T0, this is equal to a positive number that I will denote by epsilon. And now let's use again C LG bar gamma is more or equal than LG gamma more or equal than C Lg bar gamma. This implies that d G bar P gamma T0 multiplied by C, this is clearly smaller or equal to C Lg bar gamma restricted to the interval A T0, and by this inequality this is smaller or equal to Lg gamma restricted to A T0, which is clearly smaller or equal to Lg gamma, because the length of gamma will be clearly be greater than the length of gamma restricted to a subinterval. Now we want to prove that dg pq is greater or equal than a positive number. How to prove this? This is the infimum of the length of admissible curves joining P to Q, but we just proved that an arbitrary admissible curve has a length which is greater or equal to a positive number. So this implies, this inequality implies this one by taking the infimum. Since all the lengths of this kind of curves are bounded by a positive number, then also this distance will be bounded below by a positive number. Now we will use this technical lemma to prove a theorem that I announced last time. Suppose that Mg is a connected Riemannian manifold with or without boundary, then M dg, where dg is the distance function is a metric space whose topology is the same as the manifold topology. In order to prove that the pair MDG is a metric space, we have to prove that DG PQ non-negative DG PP0 and DG PQ equal DG QP. Let's write this way, and DG PR smaller or equal than DG PQ plus DG QR. This is known as triangular inequality. Okay, how to prove, for example, this one? This is immediate because by definition of distance, dgpq is the infimum of lengths of admissible curves joining p to q. So this is the infimum of positive numbers, and such an infimum can be only positive or zero. It is clear that this distance here is zero because this distance is achieved by a constant curve having length 0. This is clear because a curve joining P to Q gives you, by a simple change of parameterization, a curve joining Q to P. Consequently, these two distances are equal. And in order to prove the triangular inequality, we use the fact that an admissible curve from P to R passing by Q can be written as the combination of two curves. The first one joining P to Q and the second one joining Q to R. And it is clear that the sum of a curve sum of the length of a curve joining P to Q and the length of a curve joining Q to R will give us the length of a curve joining P to R passing by Q. And if we take the infimum of such lengths, of the length of such a curves, we get immediately this inequality here. How to prove that the metric topology coincides with the manifold topology. In order to do this, we suppose that U is an open set in the manifold topology, we have to prove that there exists a metric ball, an open metric ball, contained in U. And this will show that U is also open in the metric topology. How to do this? For each P in U, choose a coordinate neighborhood V of P with V contained in U, such that previous lemma holds true. In particular, we have that the GPQ satisfies this inequality here if Q belongs to M minus V. And then let's take the contrapositive of this. This says that the GPQ smaller than D implies that Q belongs to D. And this says that a metric ball over radius D is entirely contained into U, which is exactly what we wanted to prove. Now we have to prove that that if U prime is open in the metric topology, then it is also open in the manifold topology. So given P in U prime, we can choose delta positive such that the metric ball B delta P of center P and radius delta is contained in U prime. Then let V be a neighborhood of P, which is open, and this is important, in the manifold topology. For which previous lemma holds true. So now we choose epsilon small enough such that C epsilon is more than delta, where this is one of the constants which appears in this lemma. Then the inequality of previous lemma, that is dgpq smaller or equal than capital C times this distance here, implies that if dg bar pq is smaller than epsilon, this epsilon here, then dgpq is smaller or equal than C times epsilon, but C times epsilon is more than delta. So this inequality here says that if this is true, so if Q belongs to V and dg bar PQ is more than epsilon, then Q belongs to a metric ball of radius delta, and this implies that Q belongs to U prime. Now let's observe that this set here the set of points of V for which this is true is open in the manifold topology Why? Because this is this condition here is written in terms of a strict inequality. So we are saying that U prime contains an open set, this one, with respect to the manifold topology, and this says this is contained in U prime. We proved this later. Implies U prime open in the manifold topology. Thanks to this theorem, which says that a Riemannian manifold is also a metric space, essentially. We can transplant the language used in metric spaces to Riemannian manifolds. So we say that M is metrically complete if every Cauchy sequence in M admits a limit in M. A subset of M is bounded if there exists C positive such that dGPQ bounded above by C for all PQ in A. The diameter of A is given by the supremum of dGPQ with PQ in A. It is immediate to prove that compact connected Riemannian manifold has a finite diameter in order to prove this, you use the fact that Riemannian manifolds is a metric space, and that a compact metric space is bounded Now let's change topic and let's talk about some special Riemannian manifolds known as model Riemannian manifolds. That is Euclidean spaces, spheres, hyperbolic spaces. The property shared by these three Riemannian manifolds are that they are highly symmetric. Precisely, these are the most symmetric Riemannian manifolds we know. Let's start our presentation by giving some preliminary definitions. So let's recall that ISO MG, this is the set of all isometries from M to M. This object here is a group under composition. We say that Mg is a homogeneous Riemannian manifold if iso mg acts transitively on M. This means that for each pair PQ in M, there exists an isometry phi such that phi P is Q. Of course, if phi is an element of this group, so if phi belongs to iso mg, we know that d phi at p acts on TPM and takes value in TPM. So these are, sorry, phi of p, and this implies that the total differential d phi, that is the map whose restriction to a single tangent space behaves this way, goes from Tm into Tm. Iso PMG, this is what we call isotropy subgroup at P, that is the subgroup of iso mg of isometries phi such that phi p is P. So this is a subgroup of isometries which fix the point P. For each phi in this subgroup, we have that d phi p sends TPM into TPM, and we have that the map let me write here phi p from iso P Mg into general linear group of TPM. This is what we call representation of iso P Mg. With I P phi equal d phi p is in this specific case known as isotropy representation. In general, if you have a Lie group, then and V a finite dimensional vector space, then any map from that Lie group into the general linear group on the vector space V is known as a representation. In the special case where the Lie group is this subgroup here, we use the expression isotropy representation. M is isotropic at P if the isotropy group, subgroup, acts transitively on the set V in TPM length of V equal 1. So this is a sort of sphere in TPM. There are manifolds which are isotropic at every point. So if M is isotropic at every point, then M is said to be isotropic. The list of definitions is not finished. Let's introduce a new object, precisely the set of all orthonormal bases of TPM. Note that here we are taking the disjoint union. There is an action of this group here on OM. Action of I sub P Mg on OM. You can guess what is this action? if phi is an element of the isotropy group, subgroup, and B1, B2, Bn is a basis or is an orthonormal basis. Let's say okay, let's say is an orthonormal of TPM, then you can define phi dot B1, B2, Bn as d phi p B1, d phi p B2, d phi p Bn, and this is an orthonormal basis at phi p. So what we are doing here, we are pushing an orthonormal basis at P forward to an orthonormal basis at phi P. So this is orthonormal basis at phi P. It is immediate to check that this is orthonormal. It follows from the fact that phi is an isometry. So isometry means that phi star G coincide with G. What is phi star of G? Over two vectors. This is G of d phi. Let's put phi p here, which is p d phi pw, and this metric must coincide with this value must coincide with this. So from this inequality, from this identity here, it follows that if B1, B2, Bn is an orthonormal basis, then also this one is an orthonormal basis. Sorry. No other remarks. One more definition. Mg is a frame homogeneous if the action described before is transitive on OM. What does it mean? It means that for all p, q in M, and B, let's say B I equal PQ, orthonormal basis at I. There exists an isometry phi such that phi of P is Q and phi dot PP is a BQ, where phi dot PP means the action of phi on this basis that I described before. Now we are ready. Let me check how much time I have. Now we are ready to talk about Euclidean spaces. We already know that this is Rn with the Euclidean metric that we usually denote by G bar. Let's see how to construct the isometries of this manifold here. It is possible to prove that the set of isometries of Rn G bar is a Lie group that is a smooth manifold, which is also a group, and for which the multiplication and the inverse are smooth maps. Precisely, this Lie group acts smoothly on our manifold. So let's see how to construct this Lie group. Suppose that theta from On, the group of orthogonal matrices, times Rn into Rn is the natural action of On on Rn. Essentially, it's the action described by the following formula. If V is an element of Rn, you see it as a vector, then if A is an element of On, what is theta V? Theta V is just the product of A and V. We define the Euclidean group En has the semi-direct product Rn times On with respect to theta determined by this action. Essentially, this is the group for which the underlying set is Rn times On, and the operation of product, the operation of this group is given by BA, let's call it product, BA times B prime A prime. This is given by B plus A B prime A prime. The second entry is given by the product of the second entries. What is interesting is instead the first component, which is given by B plus A B prime. This Lie group here is a faithful representation I told you before what a representation is a map that in this case we will call rho from the Lie group, in this case En, into the general linear group on a vector space. In this case we work with Rn plus 1, and we will use the notation n plus 1 comma r. The reason why this representation is faithful is that the map I'm going to write down is injective. So what is the definition of rho? Is this rho of BA is A B01, where you write any element B of Rn as a column vector. So En acts on Rn by this kind of product. BA times X is B plus AX. You can prove, I leave this as an exercise, this action is isometric, and the induced action on ORN, that is the set of all orthonormal bases of TPRN, is transitive. Both these two properties follows from the fact that this matrix here is orthogonal. Okay, this is a good point where to stop. Thank you for your attention.